if we apply what we know towards an entire circle, we're going to be able to fill in an entire unit circle of values in radians. We already pretty much know most of these in degrees, but now we'll be able to extend it to radians. So the unit circle or circular functions can be determined around an entire circle, but specifically when I'm talking about the unit circle, I'm talking about a circle with a radius of 1 unit. So there's a coordinate point associated with the intersection of a radius and the circle itself. That coordinate point contains all of the information we need. There's a formula that's not written on here, but that coordinate point is r times the cosine of theta, comma, r times the sine of theta. But on a unit circle, since the radius is just 1, that formula can actually translate to just be cosine of theta, sine of theta. Which means as we look at a unit circle, we're going to be able to find these values of sine and cosine really easily because it is just the x and the y coordinates respectively. That's what all of that little text down there at the bottom is saying. So for today, if you're going to follow my highlighting, I'm going to be highlighting things that are cosine in red and things that are sine in blue. So if you want to follow along with me, that's what I'm going to be doing. So if we go down here to the main idea, which I know I'm skipping a bunch of text, but it's essentially what I've already explained. The main idea here is that for a unit circle, you can find the sine of theta, or the sine of the arc length, which is similar, for sine just by finding the y value, and for cosine just by finding the x value. And since that's the case, it follows that tangent, which is sine divided by cosine, would just be the y value divided by the x value. Sine divided by cosine. Obviously, x cannot be equal to 0 or else that number is undefined. Cosecant is the reciprocal of sine, so all we have to do is take the reciprocal of y, so put y on the bottom. Secant is the reciprocal of cosine, so similar, put x on the bottom. And cotangent is the reciprocal of tangent, so again, it would just flip over the tangent. So all of these values that we've defined throughout the class are still the same. If we just let r equal 1, the formulas just simplify to single letters for the most part. This will be added to your formula chart, by the way. I don't think I'm going to use the letter S. I'll probably use theta, but it will be talking specifically about a unit circle when I want just the letters. So be looking for this phrase. This is for a unit circle. Sine of theta is equal to y, and cosine of theta is equal to x. Now, just like a reference angle, and the reason this is using S instead of theta is that it's referencing an arc length, which we learned about last time. But if you think about the arc length or reference arc, like the reference angle we used in chapter 2, they're really the same thing. So we can use a reference arc length if we know it, or a reference angle, which the reference angle might be easier for us to understand since we've already done that in other chapters. Okay, if you flip the page, this is an important page. Ooh, I have my things out of order. Is this page next? Okay. Sorry, I had my papers out of order. This little exclamation point section of important things is just talking about the domains of the circular functions. I'm not so worried about this right now. In chapter 4, we'll discuss this again when we actually graph these functions. But if you're looking back and you're wanting to check if your answer makes sense, you just want to make sure it's in these domains. Again, I'm not that worried about it in this chapter. We'll talk about it again in chapter 4. But when we find the values of circular functions, we're going to use that unit circle and the idea of repetitive periodic functions to be able to find these. So number one thing, make sure your calculator is in radian mode when you're finding these circular function values because we are measuring in radian angles. But in the picture provided for you in example 1, it says find the exact values of sine of 2 pi over 3 pi over 2, cosine 3 pi over 2, and tangent 3 pi over 2. So it gives you this image. This is a unit circle because the radius is 1. Since I noticed the radius is 1, that means all I need to do is identify the coordinate point at 3 pi over 2, which is right here. I meant to circle that, not highlight it. That coordinate point of 0, negative 1 will tell me the cosine and the sine value of that angle. So without having to do any work or any thinking, since I have that coordinate point, I know that the sine of 3 pi over 2 is just simply that y-coordinate, -1. I know that the cosine of 3 pi over 2 is just the x-coordinate, or 0. Again, this is because it's a unit circle, and I have the coordinate point around that circle. If I were to find tangent at 3 pi over 2 is just the ratio of y divided by x. Hopefully your spidey senses are tingling. What is -1 divided by 0?
0.
Ooh, I've heard both. It is undefined. You cannot divide by 0. That's a knockout. So 0 on the bottom is undefined. 0 on the top is fine. That's 0. So just by having these coordinate points, again, around a unit circle, we can do a lot of trig very quickly. Let's do example 2. Again, just as quick. Now, on the next page over, so you do have to flip. Unfortunately, you have to flip right now. I want you to use the unit circle for this one. So flip over your page to find the exact values of cosine 7 pi over 4 and sine 7 pi over 4. So if you look around your unit circle to find the angle titled 7 pi over 4, it's connected to a coordinate point, yes? What's the x-coordinate of that coordinate point?
315.
Oh, that's the degree measurement, but yes, I want radical 2 over 2. I want the x-coordinate of the parenthesis guy, which is square root 2 over 2. Okay, again, we're at the same angle, but this time I want the sine of 7 pi over 4, which means I want that y-coordinate. What's the y-coordinate there? Negative radical 2 over 2. So the unit circle, super helpful because it contains these different values for x and y, and I don't have to multiply them by a radius because the radius is 1. Part B says to still use the unit circle and the definition of tangent to find the exact value of tangent and -5 pi over 3. Okay, if I wanted to do the tangent of -5 pi over 3, let me put that in parentheses. I know that tangent is the ratio of sine over cosine. So I could just find the sine of -5 pi over 3 and divide it by the cosine of -5 pi divided by 3. So that unit circle is going to come in handy to know sine and cosine. Tangent is just their ratio. So again, I can't show you both at the same time, but flip your paper over and we're going to find -5 pi over 3, which means it's not going to be actually listed on your paper because these are all the positive directions. But what you can do is count by pi's over 3 clockwise 5 times. That didn't make sense, did it? If I do this, we said the sine was root 3 over 2. Oh, that's a highlighter. Okay. We said the cosine was 1 over 2. Since it wants exact values, you can't put this in a calculator because that radical 3 would be some sort of decimal and you would get a rounded answer. So we got to remember our fraction rules. When we're dividing fractions, what is the rule? Keep, change, flip. When you keep, change, flip, these 2's are going to cancel each other out. Pow, pow. And we have square root 3 over 1, which is just square root 3 or radical 3. Which makes sense. Because if we think about that unit circle, and I'm going to flip back to the other page now, the last part here says use reference angles and radian to degree conversion to find the exact value of cosine of 2 pi over 3. Okay, this time we're not going to use the unit circle to think about it, so don't flip it over. When I ask you to use reference angles, we're trying to think about small acute angles and then the quadrant that it's in. This is just like the first gym kit I had you play today. So if I was finding the cosine of 2 pi over 3, it would be similar to cosine of pi over 3. How do I know that? Because the reference angle for 2 pi's over 3 is pi over 3. Here's your hint, pi over 3, pi over 3. My problem is I need to know if this needs to be positive or negative. What quadrant is 2 pi over 3 located? This is in quadrant 2. In quadrant 2, is cosine going to be positive or negative? negative. So I actually want to find the negative version of that. You guys have this memorized that the cosine of pi over 3 is a half, but if it's in quadrant 2, it's just negative. So it's negative a half. I didn't convert it to degrees because I want to get us used to thinking in radians, but this would be just like finding the cosine of 120 degrees. To check your work, if you look at 120 degrees, or 2 pi over 3 on the other page, that first coordinate, the x-coordinate or the cosine coordinate, is negative 1/2. So you can use the unit circle, if you have one, or if you have it memorized, or you can use the idea of reference angles to answer these questions, just depending on how the question is asked. Before we move on, because it kind of skips to a different kind of question, in examples number 1 and 2, are there any lingering questions? Okay, we'll move on. So we're going to jump 2 pages now, because the next page is that unit circle, which is a great reference tool for you. But we're going to, okay, so if I was doing this for negative 5 pi over 3, I know normally, oops, wrong thing. This would be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. But I don't want to go that direction because that's positive angles. I want to go the opposite. So this is 1 pi over 3, so negative. Negative 2 pi over 3, negative 3 pi over 3, negative 4 pi over 3, negative 5 pi over 3.
Why did you start at 0 and not at the pi over 3?
Say your question one more time.
Why did you start at 0 and not like the pi over 3?
These angles are going to be in standard position, so we're always going to start from here.
Okay.
Positive goes this direction, negative will just go this direction, clockwise. Say again?
You counted 180?
I did. So since 180 is pi, it's 3 over 3, because the 3's would cancel. So 3 pi over 3 would just be pi. So I counted 1, negative 1, negative 2, negative 3, negative 4, negative 5. Pi's over 3. So you're looking here. Yes, since we're looking here, when we go back to the other question, I'm asking you for tangent. So I'm going to end up needing both values. I'm going to end up needing the cosine and the sine. Okay, I'm flipping back to the other page. When I think about this unit circle, and I just would ask you, since I'm at this angle, what is tangent of pi over 3? You guys have this memorized. It's just square root 3. So it's the same value. We just found it using the coordinates of sine and cosine around a unit circle. So it's all things we should already know, just in a roundabout way. So we're using that unit circle, the x and y coordinates, to answer questions. I'm going back to the other page. To these questions. So if you see that the question asks you for an approximation, we need to be looking for this sort of word versus exact value. If it says approximation, it's a calculator question, and then you just need to know how many decimal points to round to. If it says exact value, you're using the unit circle or reference angles like we did on the other side. Since this one asks you to find a calculator approximation for each circular function value, it says cosine of 1.85. Notice it does not say degrees. It is measured in radians, which is why I was being so annoying about putting those degree symbols in all of chapter 2, because this looks different and it is different. So write yourself a little note here that your calculator needs to make sure that you are in radian mode, which it should be because they reset into radian mode. So as long as you reset your calculator every time, you'll be in radian mode. But all we're going to do is type in cosine of 1.85, just straight up button pressing. Cosine of 1.85, as long as you are in radian modes, is negative 0.2756. We'll keep 4 decimals. And I'm going to let you finish this. I want to see if we remember how to get parts C and D in our calculator. Okay, when we find number B, it's again just a plug and chug. We want cosine of 0.5149. We should get 0.8703 if we round to 4 decimals. But for parts C and D, you had to remember the trick to get cotangent and secant into the calculator. What was that trick? Trick's maybe the wrong word. What is that process? The reciprocal. So cotangent is the reciprocal of tangent. So we'd actually be typing into our calculator 1 over the tangent of 1.3209, which would give you 0.2552. No, does it? Yeah? Okay. And then for secant, secant is the reciprocal of cosine. So we would be typing in our calculator 1 over cosine to find that value, and again it would approximate to negative 1.0243 if we round to 4 decimals. So don't forget about typing those reciprocal values in, that they are 1 over the function. Because not only am I going to ask you to evaluate reciprocal functions, I'm also going to ask you to use inverse functions to find a number or an angle when I give you the value. So we can reverse the process used above to use a calculator to determine an angle measurement if we don't know it, as long as we know the value. These are the blue keys above sine, cosine, and tangent. So it's sine inverse, cosine inverse, and tangent inverse. That's what we're going to use to solve for an angle. It's not the reciprocal, it's the inverse. So in example 4, it says approximate the value of s, which is theta, it's using arc length here, in the interval from 0 to pi over 2, if cosine of s is equal to 0.9685. Okay, we know that if we are trying to get the angle measurement out of a function, we have to undo that function. We have to do the inverse of that function. So to find this angle, which we have labeled s in this problem instead of theta, that's okay, we just do cosine inverse on both sides. That gets rid of the cosine on the side with the angle, and we would just take the inverse cosine of the value, 0.9685. When we do that, it would tell us that my angle is 0.2517, but I do want us to check and make sure that we have found the correct angle in the interval they want for us. So the easiest way for me to tell you to do that is for you to check and make sure that this number we got as an answer is actually between 0 and pi over 2. So is it, first question, is it bigger than 0?
Yes.
Yes, pretty obviously. Is it less than pi over 2? Let's just double check. In your calculator right now, just do pi over 2, like straight up in the home screen. What is that approximately?
1.570.
Yeah, 1.5708 is pi divided by 2. Is our value that we got in between 0 and that number?
Yeah.
Yes, so we found the correct angle because we could be looking in the wrong interval. Now, again, it's going to probably have you use a calculator, and it's going to say this word approximate when the value is not something you should have memorized. But when the value is something you should have memorized, it's going to ask for exact value. Let me answer the phone, and then we'll do this question. Like I said, if it asks you to find the exact value, this is one we're not going to use the calculator for. You need to do it by hand. So it says find the exact value of s, you can think of that as theta, in the interval from pi to 3 pi over 2, so a different interval, if tangent of s is equal to 1. Okay, so not panicking here. If I find s, that means I just need to take the inverse tangent of of 1. So I think to myself, okay, what values typically in quadrant 1, if I take the tangent of that angle, it would give me 1. So if I put tangent of something equal to 1, what is that angle? 45 degrees, so in radians that would be pi over 4. So the inverse tangent of 1 is going to be pi over 4. The problem is that's not the right answer, because is this value we got in this interval from pi to 3 pi over 2? No, pi to 3 pi over 2 is quadrant 3. Can I change pi over 4 to its, as if that's the reference angle in quadrant 3? What angle would this change into? 225, but in radians? It is 5 pi over 4. Here's how you can think about this. You know that pi is 4 pi over 4. So we need to be past 4 pi over 4, which means it would be 5 pi over 4. just one more than 4 pi over 4. So that puts it in quadrant 3, which actually answers the question. So while pi over 4 is a value, we have to know what quadrant or which interval we're working with, and we were working in quadrant 3, so we had to adjust it to the quadrant 3 version of pi over 4, which is 5 pi over 4. And that makes sense because tangent is positive in that quadrant, so we knew that since it was a positive value, we'd be in either quadrant 1 or 3. 3 it was.
But why did you use 4? If it's just pi, could you use like 5 pi over 5 or 6 pi over 6?
Like here is what you're talking about? Correct. But I want to make it match the denominator I know. So naturally, you'll probably use 3 pi over 3, 4 pi over 4, and 6 pi over 6, since those are the ones I had you memorize on a chart for 30, 45, and 60 degrees. That's a great question. An interesting application of circular functions, just for in case you were wondering. An angle of elevation theta of the sun in the sky at any latitude, big L, is calculated with the formula sine of theta equal to the cosine of d cosine of L cosine of omega plus sine of d times sine of L. By the way, this is the Greek letter omega. I don't know if we've seen that yet, but don't panic, don't say W. That is omega. It's a lowercase omega. In this formula, when theta is equal to 0, it corresponds to sunrise, and theta equal to pi over 2 occurs if the sun is directly overhead. So we're talking about like a daytime, right? The Greek letter omega, oh look there, is the number of radians that the Earth has rotated through since noon, when omega is equal to 0. D is the declination of the sun, which varies because Earth is tilted on its axis. All of those things just to tell us what those variables are. Our actual question here says Sacramento, California has a latitude of L equal to 38.5 degrees or 0.6720 radians, which means all the places I have L, I'm going to change to that radian measure because it's an angle. It wants me to find the angle of elevation theta, so we're finding theta, of the sun at 3 p.m. on February 29th, 2012, where at that time, D is equal to negative 0.1425, and omega is going to be equal to 0.7854. I missed a D here. Sounds super duper complicated, but when you realize what they've given you, it is a really simple inverse trig question. So we're going to fill everything in. It's going to look gnarly, but it's going to take like 2 button presses of the calculator to answer when you realize what we were given. So I'm going to find the sine of theta, or I'm setting up sine of theta, is going to be equal to the cosine of D. D is negative 0.1425 times the cosine of L, which I make sure I use the radian version of that, times the cosine of omega. All of that plus the sine of the D value. I already ran out of space, just gonna scoot over. This is just a gnarly equation. It's okay. Times the sine of L, which again, I make sure I use the radian measure. Oh no, it didn't stick. Okay, that's a lot. But if we look at what I filled in, how many variables do I have left? 1. I just have theta left. Now, this is complicated on the right-hand side, but on the left-hand side, how do I isolate theta? Yeah, sine negative 1. The inverse sine is going to get rid of sine. So really, theta is going to be equal to the inverse sine of all that. I won't make you write it again. So we don't actually have to do a lot of solving here because we're just looking for theta. So what I recommend, or the way I did it, is I calculated all of this in my calculator first, and then I did the inverse sine of the answer. So there's a button above the negative sign that says ANS in blue. And these calculators also work if you like go up and press enter, it retypes the number, right? So it's going to send in your answer to where you put ANS, the answer from the previous. So we can calculate this theta. Now I'm going to give you a second because I want to make sure we can actually type all of this in however you want to do it. If you want to do it all at once, that's fine. I don't trust my typos like that. I need to do it in a couple steps. But I don't want to lose any of the numbers. So we're going to type all of that in, and we'll find theta. I'll give you a second. We should get 0.4773 radians. Is that what you guys got? Or did I go too fast? Okay, what if I asked you, it doesn't say it in this question, but what if I were to ask you to give your answer in degrees? How do we change this question back to degrees? So when we're doing this, sorry, it's the other conversion because we're already in radians, so we want the pi to go away. So the pi is going to go on the bottom, so it's 180 divided by pi. We would press the pi button on this one, so it would be 0.4773 times 180 divided by pi. It ends up giving you 27.3447 degrees. Now make sure if it asks you to put it in degrees that you show me a degree symbol. Otherwise, I'm assuming it's in radians. And wait to round to the very end, especially because the person grading your homework is a computer and it doesn't have the same thought processes that a human does about rounding. You have to be correct on rounding on a computer. And just in life, it's a good habit to make sure you round correctly. Okay. So the unit circle, real important. And I gave you this unit circle in your notes. But it's like in the middle of this packet, which is going to be annoying for flipping to look at. So we're going to create ourselves a unit circle using some paper plates. Arts and crafts time again.
No.
Yay!
Horrible last year.
No, we got it. We got it.